the simplest hydrocarbons called alkanes, more about their names and structures, as well as looking at some of their properties. Then we'll take a brief survey of the other categories of chemical compounds. We talked last week about having chains of carbons, having rings of carbons. Well, another variation we can have the chains, but instead of one continuous chain of carbons sticking off the chain, we can have branches. Those branches could be other carbons, or they could be things other than hydrogens like halogens. So if we have a side chain that's a carbon group, we're going to name it in a similar way that we talked about naming the actual carbon chains themselves. If you go back and look at the table from Chapter 11, Table 11.1, I believe it is, had the up to 10 carbon chains. One carbon had a root name or prefix of meth. And we had so one carbon alkane was methane. A one carbon side chain or one carbon alkyl group is a methyl group. We use the same meth to indicate one carbon. We just add a YL suffix. Similarly, the two carbon prefix is F. So a two carbon side chain will be an ethyl group. A three carbon prop will be a propyl group. We also have our halogens, chlorine, chlorine, bromine, and iodine. We just become fluoro, chloro, bromo, iodo. We also have to start dealing with the idea of isomers. We'll see several examples of this, but isomers are compounds which have the same chemical formula, the same number and types of atoms, but when we look at how those atoms are put together, when we look at the structure, there's a difference in the way things are put together. And that means that there's going to be a different name, and they're going to be a different set of properties. They may be similar, but they'll be slightly different. We'll look at one type of isomer today, which is called structural or constitutional isomers. There are also other isomers where it's just going to be a matter of how things are positioned in 3 dimensions. That'll be discussed a little bit at a couple of different points in Chem 122 for any of you taking that course. The most I can get without lifting my finger is 3 carbons in a row. That makes that a 3 carbon chain, or propane. But it's not just a 3 carbon chain. Sticking off of that 3 carbon chain is a 1 carbon side group or substituent. Since it's only 1 carbon, we're going to call it a methyl group. And so this compound, its most complete name is 2-methylpropane. They're both C4H10, but they have slightly different properties. The one on the top has a slightly higher boiling point, a slightly higher melting point. Now they both are nonpolar, insoluble in water, both are flammable. Yes?
Where did 2 come from?
In my 3 carbon propane, what that's telling me is which carbon in the propane is the methyl group attached to. The first, the second, and the third. Now in this case, you really can get away without using the 2 in this one. Because if I stuck it on carbon 1, that just extends it into a 4 carbon chain. Same if I put it on carbon 3. But just to be consistent, don't use a number whenever we can. The only big exception is we won't use it with rings. But we had a carbon with 3 hydrogens side group, that's a methyl group. If you see a CH3, CH2 connected to your group, a 2 carbon fragment connected to your main chain, it's an ethyl. 3 carbons, you actually have 2 choices. you have propyl or isopropyl. The difference is which carbon in your side chain has the connection to your parent or main chain. In the actual propyl side chain, it's the carbon at one end that's then attached to your parent chain. In the isopropyl, the connection is through the middle carbon. We also could have halogens, fluoro, chloro, bromo, iodo. Now, if you have both chlorines and fluorines replacing hydrogens on your alkane, you could end up with a chlorofluorocarbon, a CFC. Compounds used as historically as refrigerants as well as propellants in aerosol cans. Big problem is they float up into the atmosphere and react with the ozone layer. Or some halogenated alkanes are also anesthetics. One of the most commonly used anesthetics these days is one called halothane, which is simply a alkane with several halogens attached to it. I believe there's even a discussion of it in one of the boxes in the textbook. So let's talk about naming a basic alkane. Our primary system for naming most organic compounds, this will be true for the alkanes as well as the other classes of compounds we'll eventually discuss. For those of you who are taking 122, first thing you want to do is you want to identify the main or parent chain or the main or parent ring. In your structure, find the longest continuous chain or the largest ring of carbons. And that's going to be your base name for your compound. It's actually going to be the part that comes at the very end of the name. If you have a 5-carbon chain, then we'll name it as a pent. If it's single bonds, it'll be pentane. If you have a 7-carbon chain, it'll be heptane. If you have a 4-carbon chain, butane. Well, once you identify the parent chain, then you also got to identify and name anything stuck to that parent chain other than hydrogens. Any carbon groups that aren't actually part of the parent chain, any halogens, as well as in later discussions, other what are called functional groups. For the substituents, you'll list them before the name of the parent chain, like I listed methyl before the propane. If you have more than one, if they're two different ones, list them alphabetically. So if I have a methyl and a chloro, I'll actually list chloro before methyl because C comes before M. If you have more than one of an identical type of side chain, 2 chlorines or 2 methyl groups or 2 bromines or 3 chlorines, then you can use a numerical prefix like we use in naming inorganic compounds, di, tri, tetra, and so forth. But when you are trying to decide how to alphabetically list them, don't use the letter from the prefix di, tri, etc. in your alphabetizing. Use the actual first letter of the name of the side chain. So dimethyl would still be alphabetized based on the letter M from methyl. And each one you get a number. The basic role is we want, because they have this particular bonding pattern involving these elements in this pattern, we can say they're going to tend to have certain properties that are similar to each other. It allows us to start organizing some of our compounds a little bit into distinct groups. When we eventually look at the reactions that are typical for organic compounds, most reactions occur at the site of the functional groups. That's what the most reactive part of the molecule tends to be. So you will find a table listing the various functional groups. It shows examples, shows both with a diagram and with a verbal description what the different functional groups are for the different classes. Let's just run through them. Let's start with simple carbons and hydrogens. This is found, by the way, in your book on the bottom of page 437. Hydrocarbons. Hydrogen and carbon. We've already talked about the alkanes. They are characterized by the fact that all the bonds between carbons are single bonds. If one or more of the bonds between carbons in your structure is a double bond, then you have what's called an alkene. Change the ANE to ENE to indicate that you have a double bond in there. If it's a triple bond, you have an alkyne, a YNE ending. Alkynes, as in it takes alkynes to make the world work. Alkanes are known as saturated hydrocarbons. For example, ethane, 2 carbons, saturated. If I connect those carbons with a double bond, I find that in order to maintain only 4 bonds per carbon, I have to use less hydrogen. To make the second bond between carbons, I had to lose 2 of my hydrogens. And with a triple bond, more hydrogen. And I drew it the more common way with the triple bond with the hydrogen on the left for the left-hand one. What do we mean in terms of saturated? This is not saturated and unsaturated like in the discussion of solutions. Can you dissolve more? It's saturated and unsaturated in terms of, is there the maximum amount of hydrogen attached to the carbons as possible? Alkanes, there's no way you can get more hydrogen on there. With an alkene or an alkyne, you can get more hydrogen on there by breaking the double bond or breaking the triple bond. Reducing it to a single bond.
So if it's saturated, it's going to be that 2n plus 2 number then?
Mm-hmm.
So if it was saturated, it would be that 2n plus 2 number.
Correct.
If you had to figure it out.
Unless it's a ring, which is just 2n. But now, this is not the way we use saturated and unsaturated when we talk about solutions that we looked at earlier, but it is the way we talk about fats, saturated fats and unsaturated fats. Saturated fats have long carbon chains with all single bonds. Monounsaturated fats have long carbon chains with 1 double bond. Polyunsaturated fats have long carbon chains with 2 or more double bonds in the chain. Although they don't have triple bonds in the fats. So we have our alkene or alkyne with a double or triple bond. We also can have what are called aromatic hydrocarbons. Now originally the term aromatic was because many of these compounds have distinct odors. Now the chemical definition of aromatic is a bit complicated. We're going to focus on one particular structure that we see again and again in a lot of aromatic compounds. It's called a benzene ring. Benzene ring is 6 carbons, each one with a hydrogen attached. If you look at the way the structure is written right now, each carbon has only 1, 2, 3 bonds. They get their 4th bonds by having double bonds in the ring. So these are also unsaturated. But these double bonds are actually much, much less reactive than the double bonds in an alkene. Now, a simplified structure of this instead of drawing out all the C's and H's, draw the hexagon. And then we have alternating around the ring single and double bonds. The difference between these two, the positions of the double bonds. Turns out in reality, neither one's the best description. In reality, the electrons that make up these double bonds spread all the way around the entire ring of carbon as one continuous ring of electron density. That's often represented by combining these into a structure with a hexagon with a circle in the middle, representing those fused double bonds in there. So that's another way of drawing benzene. And the next structure I'm going to draw, I'll tell you right now, does not exist. If it did, any idea what you might call it?
Peace sign and
No,
carbon.
peace sign is actually
Yeah, that's true.
anyone recognize that symbol in the center?
No, it's not for Eve.
Think fine German engineering.
Oh,
This
Mercedes.
is Mercedes benzene.
Is that going to be on the final?
No. But if you come back to 122, you'll get some more good chemistry jokes. Or some of you may argue, wait a minute, we haven't heard the first good one yet. Right. Now, the other classes involve adding other elements. Alcohols. Replacing a hydrogen somewhere on the chain is an oxygen with a hydrogen, a hydroxyl group. Related to that, ethers. Carboxylic acid. Two carbons connected to the same oxygen. One's connected with a double bond, one's connected with a single bond. Same is true in an ester. Two carbons attached to the same, two oxygens attached to the same carbon. One connected with a double bond, one with a single bond. The difference is what's on the other side of the single bonded oxygen. In a carboxylic acid, there's a hydrogen on the other side of the single bonded oxygen. In an ester, there's another carbon on the other side of the single bonded oxygen. If we see a nitrogen attached to a carbon, there could be other carbons, there could be hydrogens, whatever else is attached to them, you're looking at an amine. If you have a carbon with a double bonded oxygen connected to a nitrogen, you've got an amide. Now, some of you may have seen some of these structures in other variations. How many of you have ever studied proteins? All right, what are proteins made of?
Amino acids.
Amino acids. On the backbone structure of all amino acids, there's on one side, there's an amine. On the other side, there's a carboxylic acid. In between, there's a carbon with a bunch of other things attached to it that tell us which amino acid it is. Right? When amino acids connect together to make proteins, the carboxylic acid of one amino acid reacts with the amine of another. They form what are called peptide bonds, which to a chemist are simply amide bonds. Amine, just nitrogen.
Okay.
Amide, nitrogen plus the double bonded oxygen. again,
Oh, and then when the proteins go through the Krebs cycle, don't they get converted to ketones or something too?
they get converted to alpha keto acids,
Alpha keto.
which are then converted to other intermediates of the citric acid cycle. And alpha keto acid is a ketone function right next to a carboxylic acid function. So take a look at these. Identify the classes for these compounds. First one. Well, what's up? What do we see other than carbons and hydrogens? I see an OH.
See alcohol.
Just an OH attached to a bunch of carbons is an alcohol. How about 2? All right. Give it some pointy ears and whiskers, and you got an ether bunny. Oxygen between carbons, that's the ether pattern. How about 3? An amine is just a nitrogen group attached to some carbons. That makes it an amine. It also means it probably doesn't smell very good. When fish start to smell fishy, when things start to rot, a lot of the bad odors are caused by amines. How about 4? Well, I got this CO with an OH. That's the carboxylic acid. While the one, the number 5, I got the CO and the O, but on the other side of the single bond oxygen is not an H, but another carbon group. That makes it an ester. Now there are some molecules, as you start to go deeper and deeper, where you see a lot of different functional groups in the same molecule. There are 3 functional groups that we looked at, shown in the molecule that I just drew. I've got my benzene ring, aromatic, an aromatic hydrocarbon. I've got a carboxylic acid function. And I drew it a little bit. I drew the double bond oxygen upside down and the single bond oxygen on the other side, but this is the ester pattern. This particular molecule has a common name.
Aspirin.
ASA, acetylsalicylic acid, aka aspirin.
White willow bark.
Huh?
White willow bark.
Basically, the original salicylic acid had an OH group here as an alcohol function. They added an acetyl group, this 2-carbon ester function, to alleviate some of the harmful effects of pure salicylic acid while retaining the inflammation, fighting, and pain-reducing effects of the salicylic acid. Okay. As you should be aware, we got a little test on Wednesday. In case you haven't checked, or if you checked late last night or till about 2 o'clock today, they couldn't get onto the system because a power failure shut down the Norfolk TCC server. Apparently the power went out and no one noticed it yesterday, and then the battery backup ran out because it was off for so long. And when they rebooted the system, tried rebooting the system this morning, they had all sorts of problems, so they didn't really get it up and running until this morning. So if you tried to get the TCC website from outside of TCC late last night or this morning, you probably couldn't get it.
I was getting ready to hit my computer.
If you actually came to the Norfolk campus, you couldn't get the internet at all.
They need a new computer
Right.
person here.
But last week, last Thursday, I posted information and sent out an email about a document with frequently asked questions about the final exam. What's the format? What should you study? When is it? So forth. Also posted a copy of the formula sheet. You'll get a fresh copy of that as part of your exam packet. And then I also mentioned previously that I will give you the option to come earlier in the day, either at 8 to 10 or from 10 to 12 and take the exam, or you can take our scheduled time 5 to 7. It's just if you want to do that, I need to know ahead of time so that I make sure that I don't have too many people scheduled for here. I've got more than 50 students taking exams Wednesday. They won't all fit in here at the same time. So I know at least one person in this class, and some people from some of my morning class have already emailed me. Apparently, if you're interested in the 10 o'clock, that seems to be a popular time. Not too early, not too late. It's also very popular. I know with my morning class, I had several of them who had childcare issues. There was no one to stay with their kids until they got off to school. They came here for an 8 o'clock exam. So, but I had also intended last night. I've given back to you by now all papers except any lab 20s that might be turned in today. And I had intended to get on Blackboard and get a bunch of grades up there so you can take a look at things. And so you could have an idea of where you stand going into the final exam. But still try to do it either late tonight or early tomorrow morning. Tomorrow I do not have my normal office hours because it's exam week, but I will be here pretty much between 11 and 7. There may be times I may, for example, go grab some lunch, or I may have to go run an errand. But general between about 11 and 7, I should be in or around my office. If you want to call me, email me, or come by. Also, for anyone who is interested, I do have your course average as of today, and I can let you know what it is if you want to find out. And I can also put up on the board the formula that anybody can use to figure out, based on that, what they need to get on the final to get a particular grade in the class.
How much was the final worth? Percentage?
Final is 20% of your overall grade.
20.
But whether you do it now or you do it later, let me just give you quick the formula.